All right. Okay, let's look over, because I think it's actually a lab question. You guys were looking at the galvanometers and all that kind of stuff, the internal, and we don't go that deep. That's pretty deep stuff. But here's basically, if you remember, maybe you do, maybe you don't. Oh, a nice clean board so we can get it all dirty. Kirchhoff's rules. Kirchhoff's rules. Basically, he says that, and they're pretty much based on the conservation of charge. In other words, at a junction, let's take a junction. All right. Okay. So right here at this junction, let's say we've got charge I coming in here, I1, this is I2, and I3. All right? So therefore, I1 equals I2 plus I3. And the reason for that is what goes in is equal to what's coming out. Okay? At a junction. All right. So that's rule 1. That's the junction rule. Rule 2 is the loop rule. You're fine. Rule 2 is the loop rule. And so on your from Kirchhoff's rules, the loop rule is where you guys are going to be deriving that one equation for I in your lab. Okay, and the loop rule says this. Let's say we've got let me just draw one here. Draw one here, and then we'll start the. Let's draw a funny looking thing here. Here's out of your. These are 2. Okay. There. Now let's look at the loop here. And this one is 3 volts. This one is 7 volts. And this one is 5 volts. Okay. Alrighty. Now, this is the book says here, this is your check your understanding number 4. It says, drawing shows a circuit containing 3 resistors and 3 batteries. In preparation for applying Kirchhoff's rules, the currents in each resistors have been drawn. For these currents, write down the equations that result from applying Kirchhoff's junction rule and loop rule. Apply the loop rule to loops A, B, C, D, and B, E, F, C. Okay, basically they did this. They went A, this junction B, C, D, and then E and F on the outside. Okay, now you take a junction. I forgot to put my currents in. All right, so the way they drew their currents is like this. I3, which I disagree with. Right off the bat, I disagree with that one. And they say I1. And then they've got I2 going like this. And they have I2 going like that. All right, so the loop rule, according to the way they have this drawn, let's take this first loop 1, or ABC. So for loop ABCD, for loop ABCD, then you've got the way they've drawn it. This would be plus, minus, minus, plus, And this would be minus plus like this. You follow the arrow, the way that they've got the current going. And this would be minus plus here. So if we started like at point A, we started at A, we're going to start at A, we're going to have the drops equals the adds. Okay? Or the loop rule on this one. Okay, so we start here at A. First one we run into, this is a drop. And that would be I1 times R1. Come around here. And this, what are we doing here at this 7-volt thing? Gain, because we went from minus to plus. Because we're just going to go around this way. So we've gained 7 volts. Okay? And now what do we do here? Go from plus to minus. Ah! I do that wrong. I'm sorry. Because that's where your current would go. Your current would go from lower to higher. So what do we do here? The way they've got it, the way I fixed it now. How is that one? That's a gain. So that would be plus I3 R3. Okay? And then it comes around here, and that's a gain also of 3. All right, so with that loop, we've got this. I would say that we have I1, R1 plus 0, R2 minus R3, I3, R3 equals 10. That's the way I'd rewrite that equation. Okay? And this equation here, for the junction at B, is going to be I1 coming in plus I3 equals I2. And I just rewrite that one as this. I1 minus I2 plus I3 equals 0. And then last but not least, let's look at loop BEFC. So, well, we'll just start here at point B, since that's where we're starting. So this would be a drop of I2, R2. Comes around here. That's a gain of 5. Comes around here. That's a drop. And this is a drop. Okay? So actually, I would rewrite this equation as 0 R1 plus I2 R2 plus I3 R3 equals minus 2.0 volts. Right away, I'm starting to think they've got one of them going the wrong way. Possibly. But it's okay. You got your, now we have our 3 equations. 1, 2, 3. And we have 3 unknowns. And we can solve it. I think what they wanted was write down the equations that result from applying Kirchhoff's junction and loop rule. Okay, let's see if we got him halfway. And again, it's just a matter on how you choose to do the algebra, too.
Professor, I have a question really quick.
Yeah.
Does it say in the question to determine the junction B? Does it say that somewhere, or did you just pick B?
I just picked B because it's handy.
That's where all of the...
Yeah. I mean, now, what's the only other junction that we can use that would mean anything?
C.
C. Yeah. C. And at C, we'd have, so if we pick junction C, if we happen to pick junction C, this is what we'd get. We've got I3 going away.
I2 coming in.
I2 coming in and I1 going away. So you'd have at junction C, you've got you've got I1 plus I2 equals I3, which does not equal that. So what did I do wrong here? Because those two should be the same. I2 is going to come around here. You're going in. I3 is going away. These two are right. The only thing I got wrong is I1. I don't know if that's good. For some, because I've got this all backwards, I think.
But ideally it should.
Yeah, that should be it. Okay, so let's take a look and see what they actually got real quick. I'm always a little hesitant about this stuff because it takes a long time to teach it, and I don't know how much bang we get for the buck, really. I mean, because it's just one little section in this whole big fat chapter that talks about a lot of other stuff. So I1 plus I3 equals I2 is one of their equations. 3 plus 7 plus I3 R3 equals I1 R1. That's what we've got. And their last one that they had was 5 equals I3 R3 plus I2 R2 plus 7. Yep, so we did it right. We got it set up the way they wanted. So junction C scares me, though. Doesn't make sense. Okay. All right. We've got it going. All right, good. Now, so there we go. Let's do this. Just while this is still fresh in your mind, let's try this right here, and you can work together. This will be your quiz. It's kind of a biggie. It'll get you ready for the little test we're taking tomorrow. Now, we're going to stop here in probably about 8 or 9 minutes, feel free to work with your lab group or whoever's sitting close to you. And we'll probably go over it, but we got to move on. We got to move on and finish the chapter. Okay, so here's the little problem. It says, need more practice? Got milk? Here we go. It's 2.0 ohms over here. And no, you can't come up and build it on my computer. Plus, I'm going to do that just to see what the answer is. This is 3 ohms. This is 5 volts. This is 4 ohms. And this is 12 volts. And it's going this way, though. There you go. And the question is this. Basically, find I1, I2, and I3. They said just find the, they wanted to know what is I1 going through here, going through here, got a question for you, though. Before we even get started here, I'm kind of getting started here. Do we have an I1 and I2 and I3? Take a look. Take a look. Now look. Say this guy kicks out a charge here. He's going to go through this resistor. Is there any difference between the current here and the current here?
No.
No. So that's why they only asked for 2. They're smarter than I am. There's I1. And then the only other thing we've got here, I'm saying this is plus minus like this. This is plus minus like this. I'm going to say this guy's kicking this guy out like this, big time. And these guys are probably going in a different direction. But we'll see. No, actually, they're probably going that direction. Figure out what I1 and I2 are. Just for your little quiz. I'll do the same. But I'm going to do it on the computer. Because I just roll like that. All right. Anyway. I saw Brienne. She came in all quiet and there she is. All right. And, and William came in too. I know I saw William. Yeah, there he is. Okay. Yeah, work together. I like hearing tittering. That's good. Feel free. Work among yourselves. And if you are tired of looking at my drawings, the problem is, and you happen to bring your book, it's actually on page 625.
Is equal to I1 and 1 R1 plus R2. Just making those two
Where are you getting for this series stuff? Well, the series stuff on I1. Well, from the 5-volt battery, it kicks out. It's got like 1 amp. 5 volts.
Is this
Well, yeah, he's pushing with it. No, it's still 5 volts. Because that's the power that you have there. Yeah. I mean, think of it this way. Think of it this way. Say you had a big, strong person pushing the charge, which is your 12 volt, and a weaker person pushing the charge, which is 5. When they're pushing together, you still got 12 and 5. The 5 guy didn't change. He didn't get stronger just because the 12 guy's there.
Why would it be parallel for the I2?
Because
Oh, wait a minute. Yeah, I guess. Well, just because of, like this just first square of the circuit is definitely like in series with so you go all the way around here and then just go back and whenever you're in series
Did it come out real easy?
there's a resistance.
What happens when you have the drop voltage plus 5?
And that's the only thing.
Can you take the reciprocal? That's the mean.
I don't know.
Then if it's 17, then
Truck is going to do
then now it's easy to do just
What if you can I2 is a size scale for
是比如典型的阳光闪是吧？
Or the SSR.
Yeah.
fun. I2 is just but so
你去追，去追。你追的时候，他结婚去哪里了？一起吧。年龄不是问题。
That's why,
Like, they're all the same.
because that entire route was obviously.
Did it come out to be easy?
but in this case it's two different areas parallel.
That's
So
why
when you
I
find
want the
when you find I3, then you have a parallel. Yeah. So they're both going to be one.
That's why you can't add.
And with getting kicked out from the battery. Yeah, forums. I think unless the drop data has anything plus the minus connected like on the resistor.
Right.
And then when you find I3, then you take 1 over everything and 1 over R take the reciprocals back, get the R equivalent. Here, this is I1. And this is 3 inches for I2. Yeah, the I in the center.
You're going to go to the computer.
all sorts of stuff. One thing, some of it's like buying stuff, some of it's like line reading kind of things. Word problems and crossword stuff.
Right, but if you go with the other way, the 5 and 6 or. Okay, so.
When you have everything's parallel in the current, I1 equals I2 plus I3. See what I'm saying? When they're in parallel, they just then it would be complicated.
There isn't anything else.
But you have to see the information, you have to know like something.
Yeah, you can calculate. Yeah. You'd have plenty of information. Okay. All right, I built this little. Built this City on Rock and Roll. No. Horrible song. What? A good physics movie? Oh. I don't know. Yeah, there we go. Now you can see it in action. All right. Okay, here's what. I went ahead and built that little circuit. Did y'all get 1 and 3?
Yeah.
Okay, cool. You're there. You're there. Okay, because I got 1 and 3 doing it. Now this is all, you all drew your currents going by convention. This has got the current going the way it really goes. In other words, you guys were pretending as if protons were moving, and this is actually showing the electrons that are moving. Okay? So, basically, because you guys had the current coming out the front end of the 12-volt battery, right? When actually, it's really giving the electrons a big push out the back end. Just like this guy is giving the electrons a big push out the back end here. So basically, through the 4-ohm thing, this is what I did. I just went, oh, okay, that was hard. It's 3 amps. Then I slid over here to this guy. I went, oh, that's hard. That's 1 amp. Once I built the little circuit. Okay. This is middle 2. It better be. Yes, it is. The middle one is 2. All right. Can we go? You guys had everything. Just get your mind around it. It's going the opposite. I can't do that either. But
Well, no. I know they're moving this way, but not that way. The other way.
right. So what we could do maybe is. Oh, now it's being. Oh. I wish I could. I got to bring it back in. So I want it to go the other way than it was, which would be like this.
Actually, one morning he was in my family.
Let me try that. There we go. Now it's going the way you guys had it. Because I changed my batteries around. So this is the way you guys drew it, right? So it comes out to be 1, 2, and 3. Good. Yeah. But this is the way in your mind, this is the way it's flowing. Okay. Good. Good. So 1 and 3. Good. We'll collect those at the end of the hour. Now, let's talk about, we talked a little bit about internal resistance. We talked a little bit about, let's take a look at capacitors in series and in parallel. Then we'll look at the time constant. You did in the lab, trust me, in the lab, they beat you up pretty good on doing the internal resistance or how that galvanometer works, all that stuff. It's pretty complicated. And I'm not being sarcastic. It is pretty complicated. Okay. So, let's take a look at capacitors in series and in parallel. And maybe do one problem. Now, oh, I forgot that maybe Friday I'll have examples of folks were asking me, how do you discharge the capacitor? Sometimes it gets so much charge it just shoots over by itself once it builds up to a certain point. Sometimes when it gets, that force gets strong enough, the electric field gets strong enough, something slides in there or the force flips a switch that closes it, and so that it discharges. But anyway, let's take a look at capacitors in parallel. Now, when we put things in parallel, here's the key. Here's the key to this whole thing. Capacitor, voltage. Capacitor. All right. When things are in parallel, if this is 12 volts, what's the potential here on that capacitor? They're in parallel, so what would it be? 12 volts. When things are in parallel, the voltage is the same. Okay? Two things that are in parallel, the voltage is the same. So this would also be 12 volts. Now, let's look and see what a capacitor does. Let's say this is C1 and this is C2. And they have different farads. They're different capacitors. They have different, and what do capacitors do? They store charge. What's a battery do? It stores charge. Basically, your cell phone, when you charge it, you're just putting charge, you're just putting a bunch of electrons on a capacitor. Okay? And then every time you key your handset, you're discharging a few electrons so it'll work. All right? So that's what you're doing. All right? So, do you all remember? We kind of went over it. So the amount of charge that's stored on a capacitor is equal to, remember? CV. Okay? The amount of charge stored on a capacitor is equal to CV. So on C1, so Q1 equals C1V, Q2 equals C2V. Notice the V is the same in both these, whatever the voltage is. But since the capacitance is different, the charge stored on them will be different. Let's put 5 on this guy. A little bit. So the capacitance is bigger. If C2 is bigger, then I can put more charge up there. All right. So, how do we do this? So the overall thing, the total charge is equal to the capacitance in parallel times V. Okay? The total charge on this thing would be, and the total charge, Q, equals Q1 plus Q2, which CPV then equals C1V plus C2V. So when they're in parallel, CP equals C1 plus C2. That's a little different than resistors. Resistors, when they're in parallel, it's 1 over R plus 1 over R2 equals 1 over R parallel. All right, now, let's get them in series. Let's see what happens when they're in series. Okay. So here we go. When they're in series, we got this kind of situation here. All right. Now, the amount of charge when they're in series is the same regardless of the capacitor. So in other words, the amount of charge is the same regardless of the capacitor. So in other words, if this happens to be C1 and C2, the amount of charge here, Q, is equal to the amount of charge here, Q. Okay? Because here's what happens. Here's what happens. A bunch of, let's take the microscopic view here. Let's just take this one capacitor on this side. Now, so we know really what's happening is by convention, we say a bunch of positive charges building up there. Actually, that's not what's happening. A bunch of electrons are building up here, and so it would be the other way. But by convention, we're saying a bunch of positive charge starts building up on here. So what happens to the equivalent positive charge on this guy? They go away. They run away, right? So in other words, say this was 10Q, just for argument. Say this was 10Q, then 10Q over here run away. And where do they go? They run away over to this one. So those 10Q come over here. All right? And so that's why the charge is exactly the same. Ten. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. Okay? So this is in series. This is when your capacitor is in series. Good. Now, so what does that look like? So if we put the capacitance in series, I'm going to go ahead and erase this over here. And we wind up with this situation. All right. There we go. Now, we've got C1 and C2. Okay, now I've got a question for you. Are V1 and V2 equal to V in this situation? Things in parallel? Or things in series? No. Only in parallel. In other words, V equals V1 plus V2. Okay? In other words, V equals V1 plus V2. All right? And V1 equals Q times C1. V2 equals Q times C2. Now, what is the same? What is the same is that the charges are the same on there. And so the total capacitance for this guy, the total charge, Q times C with them in series, which is equal to that V there, is equal to Q. This is not right.
V equals.
Why did you let me do that? Q is equal to V, C1V. I knew I was in trouble right when and C1V1. And so V1 is equal to Q over C1. This is the same mistake I made before. Q equals C2V2, and V2 then equals Q over C2. So this is what I'm trying to get. So I get V then, which equals Q over CP. There we go. Q over CP in parallel equals Q over C1 plus Q over C2. I can divide out the Q's, and I wind up with 1 over CP equals 1 over C1 plus 1 over C2.
That means series, yes.
Yes? I still got resistors on the brain here. So capacitors work just the algebra for capacitors is just the opposite of the algebra for resistors. Now, let's do a problem, just to hammer this point home. And sometimes I assign this problem, but I didn't this time. Just to give us an idea of how this works. And then we'll get to the time circuit, and that's a lot of fun too. Where are the problems? Here they are. All right. What the heck? Why not? And then we'll actually do two problems with resistors here. So we've beat ourselves to death with Kirchhoff's rules. You got that little quiz just fine. So here, we're going to run from A to B. This is a part of a circuit. Got microfarads here. Four microfarads here. Two microfarads here. 12 microfarads here. And 8. Oh, that's not 2. 24. So I got the rest of them right. Oh, there's one here. Gosh. Physics being taught by Mr. Magoo here. Okay. There. All right, now we got it. Determine the equivalent capacitors between A and B for the group of capacitors in the drawing. All right. What do you think we're going to do first? Look at the ones in series back here. Yeah. We'll start with the ones in series back here, make that an equivalent one. Then we'll say it's the same thing as being in parallel to this one. And then we'll bring it all in, and then we'll look at the ones in series. Okay? So we're going to look at these three guys first. That's where we go first. And they are in series, so they are 1 over CS equals 1 over 24 plus 1 over 12 plus 1 over 8. Thank you for being common. So we've got 1 over 24 plus 2 over 24 plus 3 over 24 equals 6 over 24, which equals, now we flip it over. So that's nice. What's 24 over 6? 4. So that's good. All right, so we've got, so now we're left with this. There. And this will now be 4. And this will now be 4. And this is 5. And this is 6. All right. So we've got these guys in parallel. So I'm going to just take those in parallel. And that's nice. All I have to do is add them. So now I'm going to look at these next step. Look at these two. And for circuits in parallel, all I got to do is add them. So that we wind up with 8 microfarads that way. So now my new circuit looks like this. Got 5, 6, and 8. And then once again, we're in, oh my, 1 over 5 plus 1 over 6 plus 1 over 8. What's the nearest one? 120? Is that the nearest common denominator? I think that's the best we can do. So we'd take 120. divided by 5 is 24. So this would be 24 over 120. What's that? It's about 0.49? Okay. 20 over 120 plus 40 over 120 equals 60. I must have done this wrong.
That's right.
This is all right so far? No.
The 8 is 15. So the 40.
Yeah.
Where? Oh, this is 15? Duh. Because it's smaller. What was I thinking? Yeah. So now, because I knew what Kurt was saying, it's got to be pretty good. 44. That's 59 out of 120. Yeah. Boy, we're real close to 0.49. And flip that sucker over, and the total capacitance is around 2. There we go. All right, now, I want to show you one other problem, or kind of with when we got capacitors in conjunction. One last thing. What's the energy stored in a capacitor? You remember? The energy is equal to 1/2 CV squared. Keep that in mind. Especially when we start going to energy densities. Now, in your notes, make sure you say energy so you don't get confused and go, oh, the electric field. Because, again, even though you guys have been doing this now for a total of 17 days, and you should be experts by now. 17 days and what, 4 labs? Or is today the 4th lab? Today's the 4th lab. Okay, so today's the 4th lab. No, it's a 5th lab. Oh my. Time flies when you're having fun. So make sure this is energy. So you've done 5 labs, 5 electricity and magnetism labs in 17 days. Think about it. It's hot. Oh, it's terrible. Okay. That's okay. That's okay. All right. So that's why we do group tests and everything else, so that you're actually learning this stuff. Because you all seem to be getting along pretty well and watching the lab groups kind of work together. And just remember, my boy Osan has your back. All right? He will take care of it. Now it's on YouTube. It's going out to the world that Osan is a fair man. All right. All right. Let's take a look at this one problem. I kind of like this one. It's actually this one. It looks like this. We're going to combine what we know together here. All right? And got a circuit that looks like this. 12 volts. R2. 2 ohms. And then, but back here, I've got a C equals 9.0 microfarads. Microfarads. Okay, good. Now, the question is this. The question is this. How much charge is going to build up on, how much charge is going to build up on that capacitor? Now, here's what happens. Here's what happens. Eventually, let's say we got a switch like here. We haven't plugged this capacitor in yet. Okay? So nothing's happening, right? Battery's dead. Close the switch. Boom, now the battery goes, oh, starts pushing charge. By convention, it starts pushing protons. All right? So you got a current going through here. And what about the current going through here? Is that equal to this one? Well, wait a minute, we got a junction here. Now here's what happens. And it happens pretty quickly. At the very beginning, we have a current here, I2, that is not the same as I1. Because we actually have an I3 going off this way. Right? We've got some charge moving over here. And so the charge moves over here, it starts to build up. This starts to build up. Okay? And eventually, this gets so built up, guess what happens to I3? It stops. It stops flowing. Okay? So all of a sudden, when I3 stops flowing, now, does I1 equal I2? Yes. So now we've got a circuit that's just going like this inside here, and this is all nice and charged. Okay? So we just have this guy kind of running. So this is the same thing as I1 right here. So now my question is this. Is the voltage here the same as the voltage here? Are these two volts equal to each other? The change, the drop here and the difference in potential here. Are they the same? Are they equal? They're equal because they are in parallel. Whenever anything's in parallel, and once the current stops flowing, or even if the current is flowing and there's no capacitors in there, then the voltage is the same. All right? That's why we hook things up in parallel, so that we can get the same voltage. So that that's why the circuitry in your house. We want to make sure that the washing machine gets that 110 volts or 117 RMS, as John reminds us, and your stereo gets 117 RMS, and everything else gets. Now there might be different appliances hooked on certain circuits, smaller appliances, and things like that. But for the most part, which would be in series. That's sometimes when you get a fuse to blow, too. Okay. All right. So let's figure out. We want to know Q. That was the question. So what we've got to do is we go, oh, okay, well, then since it's just this flowing through here, I know this. I know that 12 volts then equals I1 times 2.0 plus I1 times 4.0 See, what I'm trying to do is I'm trying to figure out what the voltage here is. The voltage at the 4 ohm place. I want to know what that is. And I can get that once I find out what I1 is. And it looks like I1 is equal to 2.0 amps. And so the voltage at the 4 amp place is equal to 8.0 volts. Because that equals I1 times 4, which equals 8.0 volts. Now I can do this. Now I can go, okay, this will be 8 Q equals CV. Will equal C times V. I've got two numbers that I can multiply together. I've got 9.0 times 10 to the negative 6 farads times 8 volts. And that comes out to be 7.2 times 10 to the negative 5 coulombs. And if we wanted to go one step further, we could say, we could divide that by 1.6 times 10 to the negative 19 electrons, and we can wind up with the number of protons that moved over there, that are on there, if we wanted to. The actual answer is 7.2 times 10 to the negative 5 coulombs. But that's what capacitors will eventually do. That's why they kind of left this thing off a little bit, that there's a current going through here. Because actually, eventually, these capacitors, unless, the nice thing, we usually use capacitors with AC circuits and stuff. We use them with DC too. Well, in fact, your cell phone is DC because it goes straight there and charges up and shuts down once it gets enough charge. Because eventually, the current is going to stop flowing. If you've got a DC circuit with a capacitor, the current will eventually stop flowing because it's got nowhere else to go. It gets so much, by convention, it gets so much positive charge built up that the rest of these positive charges don't come here anymore. Yes?
Is there a reason to have capacitors in series?
Everything, yeah, I'm sure there is. I can't think of one off the top of my head. But everything has, yeah.
And how do those discharge? Like, would they discharge together, or would one?
They'd probably discharge together. Yeah, there's enough force there or something where they discharge at the same time. Find that out. Okay. Last thing. Ooh. Yeah, I'm sorry. Last thing. And this is a real headbanger, too. All right? I apologize for this one. But anyway, this is going to be time series of a circuit. Time series of a circuit. And basically, here's the deal. Based on your picture there in your book. All right. This is an RC circuit. We got a little resistor, got a little capacitor action here, got a voltage. Okay? Got a voltage. Big voltage. All right. Got an R, got a C. Now, eventually this thing is going to charge up. Okay? Eventually this thing is going to charge up and the current will stop charging. And what we want to do is the max, Q max, is equal to C times V naught. We'll make that a V naught right there. Okay? But in the interim, the amount of charge that's on there, Q, is equal to this. It's equal to Q naught times 1 minus e to the negative t over RC. I'm just glad you stuck around to the bitter end. Little exponential function here. So when t equals 0, what does that function equal? Oh, careful. What does it equal? Yeah, it equals 0. When t equals 0, Q equals Q naught times 1 minus e to the 0. What's anything to the 0 power? 1. Yeah. It's a trick question. The rest of you are looking at, oh, when t goes to infinity is what you were doing. I know that's what you're doing. So when t goes to infinity, that's good. Now, let's take t goes for a long time. Okay? Like one of your lectures. All right? So we get Q equals Q naught times 1 minus e to the, well, I'm going to do it this way. 1 over e to the infinity over RC. Okay? And so when anytime you got something running to the infinity in the denominator, what happens? Goes to 0, so this equals Q naught. There you go. That's what y'all are doing. It said, oh, it equals Q naught. Because at 0, it's charging up. Okay? It's charging up. It has no charge yet. And then get it to keep running. All right? And then what happens is we get it all nice and charged up, and here's what we do. Take that battery out. So this is all nice and charged up. Boom, boom. And here's what happens. Boom. The current starts to flow. Again, by convention, it starts to flow this way. I. And it runs through the circuit, and then it dissipates out, and it's done. And so now the charge will go down to 0. This is when it's discharging. Q is just equal to Q naught times E to the negative T over RC. Okay? That's discharging. This is charging, and this is discharging. So eventually, as T keeps running on, this thing goes down to, back down to 0 again. Yeah. Because I wind up with a really large number in the denominator once again, and so therefore it goes to 0. All righty. Well, that wasn't too bad. Trying to think if there's anything else for tomorrow that you need to know. It'll just be over chapter 20. I really kind of like those questions on resistance and resistivity. Did you happen to notice that in your lab they do a lot of stuff with temperature? And our book never mentions temperature hardly at all. Well, I don't mention temperature hardly at all. Because all of this stuff, one last parting shot, all of this stuff depends on how cold or how hot the material is that you're working with. Because if we can get things down, we don't need batteries when we're dealing with superconductors. Superconductor, you get a charge going, it'll just keep going forever. Okay? Might be going, well, that's cool. Why don't we make things out of that? Well, the problem is it's got to be at 3 to 4 kelvins for it to work. And so that'd be kind of a chilly house. Okay, if you're at minus 271 degrees Celsius. All right, so right now, they do have things that they call them warm superconductors, and those are only at a minus 150 degrees Celsius. So we're getting there. We're getting there. All right, but everything, materials, anything with materials depends on temperature, because temperature really tells you how much energy is in the material and how much energy is flowing around. So that's why, and plus all the scientists downstairs that I work with are all materials kinds of guys looking at that stuff. So that's why they emphasize. So suffer through, you'll be fine. The labs actually get easier once we get the light and wave. Okay? So we got about 2 more tough labs, and then they kind of get easier. All right. Have fun. I'll see you on Friday, and you'll have a good time again.